Hi, thank you for the invite to speak. Very pleased to be here. I'm going to tell you about one experiment that we have run looking at ketamine and functional imaging with a single dose where we've scanned people just after 2 hours, which is when the earliest evidence of antidepressant effects seems to occur within those hours. We chose to look at remitted patients with depression because we were quite interested in understanding what the neural effects were in those early phases without the potential confound of symptom changes. Because, of course, any changes we see in the imaging could be a direct psychopharmacological effect of ketamine, or it could be secondary to symptom changes, which, of course, one must consider when doing functional imaging with tasks. Okay, so that's what I'm going to tell you about. I'm going to thank people first. So Vasilia ran the studies. Indaba, in his bike helmet, is our physician in the group. Steph's the nurse, and Pete Hawkins also helped devise the analysis. And we had some collaborators, and we had some money. Great, always good. So I'm not going to read this slide, by the way, but we know that dysfunctional reward processing is associated with depression. And we know that you have overgeneral memory recall, and we know there are affective biases. So this led into the decision for one of the tasks as well. We also know that ketamine almost certainly induces plasticity in the brain as part of its therapeutic mechanism, and that probably occurs over days, but it also can occur quite early on. And over those days, we see changes in brain activity and connectivity. And there are some studies in depression looking at memory recall showing changes in connectivity, hyperconnectivity usually, with structures such as the amygdala. So the amygdala was an important ROI in our study, as was the posterior cingulate cortex. And we also know that ketamine can improve anhedonia. So we've chosen just a straightforward task of reward processing to target that. And there's some references there. But what we don't know is how ketamine might actually affect the brain processes associated with autobiographical memory recall. Possibly reconsolidation, but we haven't gone that far in this study, but that's, of course, the theory about where that might be going. We also don't know very much about those very early time points as well. So that's the background that tells you why we've chosen the elements of our study design. So we've got a hypothesis that we'll see modulation of activity in areas associated with autobiographical memory recall, as well as connectivity with the amygdala and the posterior cingulate. And we didn't really have much data on this, but we hypothesized that the valence conditions will show the biggest effects, because they show the biggest effects in patients with depression and also remitted patients with depression. And also we looked at a reward processing task, a monetary incentive delay task, which has been used a lot. And we expected to see modulation in that task as well. Okay. So we had 37 people in the study. They were all symptom-free at the time, and they had a 40-minute 0.5 mg/kg infusion. And a couple of hours later, they had their MRI scan. It's a placebo-controlled study, fairly straightforward. So what happened subjectively? We got dissociation, as you expect, and this is the psychotomimetics states inventory. And you can see the total score increased, and the scores are quite low, but every subscale also increased. We looked at the plasma levels and the metabolites as well. And as you'd expect, the levels of ketamine start off quite high, which is the blue bar, and then a couple of hours later, which is the orange bar, they drop, whereas the metabolites go up, as you'd expect. So we had those available to look at correlates with the imaging data as well. So the MID task, I'll just spend a couple of slides on this task because it's published earlier this year. So if you don't know the task, it's a reaction time task. Every time you see that white square on the screen, you have to press a button. I won't do the task for you today, but you have to press a button, you can relax. And it's preceded by different cues which indicate the probability of a reward that could be delivered if you responded fast enough. Okay, so you've got to pay attention and press buttons. And people win some money, and then we give them some money. So it's all good news, really. Okay, so sorry, busy slide, but we can split the task into two phases: anticipation, when you're waiting to press that button, and the feedback, which is when you found out if you won reward or not. We see some changes, but very subtle, when you're anticipating the potential to win a reward. And these are our regions of interest. The striatum is a key region of interest because it activates beautifully with this task. And we see a significant increase in dorsal striatal activity, but no other changes across the striatum. It might look like there are some other changes, but none of them are significant. The little crosses above the blue bars are the areas of activation that were significantly different from 0 on the placebo, and the asterisk is the drug effect. But during feedback, we saw a lot more modulation. We saw big increases in dorsal striatal and ventral striatal activity on ketamine during feedback, particularly on the low wind trials. And in fact, it sort of made the low wind trial activity look a bit like the high wind trial feedback activity on ketamine. And we also saw some modulation of the insula during the high wind trials. And also, we saw this change in the ventral tegmental area. And I highlight this because this correlated with the 2R, 6R hydroxy norketamine levels taken at the same time as the scan. So that's an interesting indication. It's a fairly small sample, so we'd like to see it replicated, but it does suggest that some of these effects may be mediated by the metabolite levels. There were no correlations with the norketamine levels. So the autobiographical memory task, we call VAMP. This task involves, I've gone too early. If I go backwards, oh, look at that. This task, first of all, involves quite a long interview with our participants where they go through different life events. And the structured interview pulls out some life events which are time limited to a single day in the past year or two. And they share the same amount of detail for positive, negative, and neutral events. And then what we do is we draw statements out from those experiences, and we train people up, but we ask people to think about them in the scanner. So we give them a statement, like your mum's birthday, and then you have a true or false question. It was a beautiful day. So the event was real. The question could be true or false, just to make sure they're paying attention. And then we give them 12 seconds to think about it with that on the screen, which we call the retrieval phase. And then they rate subjectively whether their recall, they consider more positive, more negative, or if it's the middle, more neutral as well. So we actively, on the study day, get the valence. We don't take the valence from the previous memory recall. Okay. So we did standard memory tests a couple hours after ketamine, like the list learning and Webster memory style, and these don't change. There's no change in overall encoding and recall of memory. We don't get behavior from this task, of course, because they're just lying in the scanner thinking about these memories. And we get this lovely network when people are recording memories, which overlaps with the default mode network and fits in with what you'd expect from the literature. I got some ugly pictures now to show you for connectivity, but I'll take you through them very quickly. So when we compare positive versus neutral memories, and we look at connectivity with the posterior cingulate, we don't see loads, but we do see lots of connectivity with the amygdala, and we see increases, particularly the posterior parts of the default mode network, and some decreases, which are mainly in the medial temporal lobes. We see a fairly similar pattern, but not as strong, with negative memory recall. And the connectivity amygdala during positive recall is a lot stronger than the negative memory recall. Okay, that's all you need to remember from that. The valence ratings don't change on ketamine, so ketamine doesn't alter your memory, the valence when recalling an experience. But it does alter the connectivity with the amygdala. We see a lot of decreases in connectivity, sort of decoupling with these posterior structures, particularly during positive memory recall, and some increase in connectivity with some temporal lobe structures. And we see a slightly different pattern of connectivity change with a negative recall. But I've pulled out the main results that overlap both the positive and the negative recall, which is in the post-central gyrus and in the superior frontal gyrus. Don't know what the post-central gyrus result means, but the superior frontal gyrus is strongly connected negatively with the amygdala. So it does fit in with an inhibition model of what ketamine may be doing during the recall. There are also some changes in connectivity which occur only on the negative memory recall, which is mainly hippocampal default mode network. And there's some areas that change only with the positive memory recall as well. But I haven't shown these for brevity. So in conclusion, we're able to show that as early as a couple of hours after a ketamine dose is administered, you can see changes in reward processing networks, mainly during feedback. And you can see changes in connectivity during autobiographical valence, autobiographical memory recall. And that fits with maybe emerging theories of how ketamine might be, how cognitive processes may be mediating ketamine's therapeutic effect through reward processing and memory reconsolidation as well. So thank you very much.
Thanks very much. Really interesting talk. So we have a few minutes for questions. Yes, Mike.
Thanks, Mitul. A really great talk. So the MID task, did ketamine change the behavior?
No, it didn't. No, they won the same amount of money.
And yeah. What do you think is going on then? What does the differential activity mean about how ketamine's affecting when people do that task?
Yeah, I mean, it's the increase. What we're seeing, the strongest result there was that during the low winds, the activity was increased. So it was similar to activity during a high wind. So we can speculate that we're sort of bringing a bit more salient. I don't like to use the word salience, but anyway, maybe it's a bit more salient, the low winds, compared to on placebo. But during the feedback, so it could be increasing the subjective value of the rewards. But behavior is tricky in MID because, of course, we manipulate the task to maintain similar behavior throughout, of course. So the behavior is not a good index of what could be happening. The imaging is probably a better index.
Just look at difference in reaction time between neutral and rewarded.
Yeah, so you're a little bit faster during the rewarding conditions, but that doesn't differ with ketamine either. Yeah. Celia's got a question.
Oh, Celia, sorry.
No, I just wondered how you interpret, again, back on the wind.
All right.
How you interpret the 2R, 6R, H and K. Why that, not the S? Because I guess the S enantiomer's got more opioid activity. So yeah, I just wondered how you interpret. What do you interpret it? No.
Well, Carlos will answer the question. He's offering to answer the question. Celia's asking why did. I'm paraphrasing. Why do we see the effects in the 2R, 6R, not the 2S, 6S? Because the 2S, 6S might have more opioid activity. I think the levels are very low. And
done
2 hours.
Well, we have CSF data that the 2R, 6R goes up.
Yeah, it goes up in our plasma data.
Yeah. Probably around that time. So
Yeah.
I'm not sure how that would help. So we have that data.
Yeah, but no, I don't know. I think we should be cautious about that result because it's one metabolite out of many, one region out of many, but it's interesting. Yeah, so sorry, a non-answer.
Was there, yeah, okay, final question.
Mitul, regarding your first conclusion, the between the medulla and hippocampus. Which pathway do you think is more probably that ketamine is connecting these areas, neurotransmitters, HPXs, receptors? What your point of view?
Well, you've got a rich innovation of serotonergic receptors in those, in the amygdala in particular. I mean, the glutamate system is the obvious candidate, but in autobiographical memory recall, I don't know. I'm trying to think of
Why receptors, maybe?
No, I don't know. I haven't thought about glucocorticoid receptors. I'm sorry, Mario. But we could do a study. We could try and block it with a GR antagonist and see if it happens. Yeah.
Move on, but thank you very much. Thanks very much, Mitul.